Hello everyone. I hope you all are doing good. Welcome to the section. This is Lakshmi Narayana, Senior Physics Faculty. Okay. So we are on time. Let's wait few more seconds to others join this class. If you have any doubts or any queries, please comment in the comment box. Okay. So just wait few seconds before starting the class, and before the class what we discussed earlier, just recapitulate everything and just few seconds, or else guess which topic we're gonna start today. What is the topic is pending, which we gonna start today? Any guess? Hmm? From the comment section, any guesses? Hmm? Any guess? Yeah. So without any delay, can we start our session? Yeah. Welcome to all. And today topic is magnetic effects of electric current. Okay. It's a very interesting topic. Magnetic effects of electric current is that it's a challenging topic first of all, because we know about electricity and we know about magnetism, but combination of these two, okay, electricity, magnetism, it's a challenging, because studying electricity is okay one way, studying magnetism is one way, but combined when it comes together, it's a challenging for every student. Okay, it's not only the student, it's challenging for the teachers also to explain in a better way. Okay, so let's see what are the topics we're going to cover. What are the topics we're going to cover in today session is that the introduction. Okay, so what is the relation between electricity and magnetism? First, if you know about what is electricity, what is magnetism, what relation is there in between these two, that we will discuss in the introduction part. Then after, magnetic field. Okay, magnetic field and magnetic field lines. If you take a magnet, around the magnet, the magnetical field lines are there, right? So properties of that and behavior of the magnetical field lines we will discuss here. Okay, and next, magnetical field due to a current carrying, okay, current due to current carrying conductor. Magnetical field due to current carrying conductor. So if you take a current carrying wire, how the magnetical field, okay, so those relations we will discuss in this topic. Next, magnetical field due to current through a straight conductor. Magnetical field due to current through a straight conductor. If you take a conductor, a straight one, how the magnetical field will be? Okay, if you changes any shape, how it will be? Okay, next, right hand thumb rule. Next one is what? Right hand thumb rule. Right hand thumb rule. Okay, right hand thumb rule. So what is the use of the right hand thumb rule, and which purpose we use right hand thumb rule? Yeah. Next, magnetical field to current through a circular loop. Okay, if you take a circular loop, throughout the circular loop, how the current will be, how the magnetical field will be. Okay, so first, if you know the relation of electricity and magnetism, then this all the topics are very easy. Next, magnetical field due to a current in a solenoid. What is solenoid first of all? Then after, if a current passes through the solenoid, how it behaves? That thing we will discuss here. Next, force on a current carrying conductor. Force on a current carrying conductor in a magnetical field. If you take a magnetical field, in between the magnetical field, just you place a one conductor. How this conductor behaves? Is there any force acting on the conductor or not? That we will discuss in this. Next one is the domestic electrical circuit. Domestic electrical circuit. So if you constructed a house, how you give a electricity through that? you need to get a permission, okay, or you need to uh, take a lot of things and all, right? It's not in easy to give, right? From battery to any electronic equipment, it's not simple like that, right? So how we give a electrical city to the constructing house or domestical purposes and all. Okay, these are the topics we're gonna discuss in today's section. Can we start with any without any delay? Yes. Let's see here. By looking the picture, what do you understand here? What do you understand here? By looking the picture and all, is there anything in your mind? Is there anything in your mind? Just take quick seconds. By looking the picture, what you understand here? See, there is a plug key, okay, and here it is a battery. From the battery, let us consider I is the amount of current is coming, and it passes through the ammeter, and it passes through the resistor also, and it is passing through the XY wire. It passes through the XY wire. So whenever electricity passes through the conducting wire, what happened here? We place a magnetic needle. Here we place a magnetic needle. So magnetic needle is nothing but a needle made up of a magnet. Okay, if you take compass, what it is present there? Magnetical needle is there, right? So in the magnetical needle, showing some deflections, whenever through the wire current is passes means, okay, when current is passes through a wire, if you place a magnetical compass, in the magnetical compass showing deflections and all. So why it responds deflections and all? Why it shows the deflections in a magnetic compass? Is there any relation between magnet and electricity? Who explained this all the things to us? How they can find out the relation between electricity and magnetism initially? Hmm? So you know, I should experiment, right? Whenever electricity passes through the wire, there is a compass under the wire. Okay, if electricity is passing like this, under the wire there is a compass. There is a compass. In this compass showing deflections like this. Then the Oersted said there is a relation between electricity and magnetism. Before that, they treated that electricity is a one topic, magnetism is another topic. When in the experiment of Oersted, they have a relation between electricity and magnetism. What relation is there? What relation is there? Remember the point. What relation is there? Whenever current passes, whenever current passes through through a conducting wire, through a conducting wire, it produces a magnetic field. It produces a magnetical field. This is the relation of Oersted experiment. Okay, in the Oersted experiment, what they said, if whenever the electricity is passes through the wire, a magnetical field is produces. Okay, okay, if electricity passes through me, I also produces a magnetical field. If electricity passes through this material, this is also produces a magnetical field. So that means whenever electricity passes through the wire, it produces a magnetical field. Clear? Clear? The electricity, in the chapter of electricity, what happened? We connected to the battery, right? Battery through conducting wire we connected. Through the conducting wire, electricity passes. So electricity passes means movement of electrons or movement of positive charges are there. So moving charges. These moving charges produce a magnetical field. Moving charges produces electricity. Through the electricity, what you will get? Magnet. Okay, magnet you will get. Next, see how the magnetical field will be. Let us take a bar magnet here. Let us take a bar magnet. It is having a north pole, and this is the south pole of the bar magnet. You see in the you see the bar magnet in a lab, right? Like this only, na? Bar magnet. What we call this is that bar magnet. We have types of magnets: bar magnet, horseshoe magnet, ring magnet, disc magnets are there. Okay, this is the bar magnet. How many poles are there? Two poles: north pole, south pole. Okay, if you divide the magnet also, if you break the magnet also, whatever you do, the magnet always existing with the two poles. Okay, north pole, south pole. See what they did here actually. What they did here, if you place a iron fillings, iron fillings, okay, iron fillings around the magnet, around the bar magnet, what happened? It produces a field. See how it look like. How it look like? It's like a field. Na? Where to where it is traveling? Where to where it is traveling? Where to where? Tell me, anybody from comment section. Where to where that magnetical field lines are traveling? Look at here. Look at here. Where to where it is traveling? North pole of the magnet to south pole of the magnet. Okay. See how iron fillings are attracting that magnet. If there are no iron fillings, we cannot see the magnetical field lines, right? So the magnetical field lines are an imaginary lines. An imaginary lines we cannot see. We cannot see that lines. Okay. For suppose if someone is slap you, can you see the force? You feel it, right? We cannot see the force. So here also, okay, so here also the field lines are exist. When we can see these field lines, if you want to see the field lines, okay, arrange the iron fillings, arrange the iron fillings around a bar magnet, and this bar magnet creates the field lines. Okay, if you want to see better, look at here. Look at here. Here I am taking a bar magnet with the pole of south pole. If I place a magnetical compass, look at magnetical compass. Look at the magnetical compass. See, if I am taking a magnetical compass, which pole it is? North pole. And south pole will be like this. Okay. And similarly here, this is south pole. And again here, north pole will come. Again, south pole is like this. Again, like this. Again, like this. Again, like this. So, the arrangement will be, see, look at the arrangement. Finally comes to here. Finally comes here. Which pole is here? North pole. And which one it will be? South pole. Okay, look at that. North pole towards. North pole towards. South pole away. North pole towards. South pole away. Look at that. Look at that. It forms a, see, from north to south. North to south. North to south. How the field will be? Outside. Okay, from north pole to south pole, how the field will be? Outside. And south pole to north pole, south pole to north pole, that will be inside. Inside. So compare these two. North pole to south pole, how it will be? Outside the magnet. And what about inside? Where to where travel? South pole to north pole. It means it forms a completely a loop, na? It forms a curved loops or curved lines it forms. Look at here. Look at here. See, if you mark all these things, you will get like this only, na? Where it traveled, magnetical field lines traveled at north pole. See, see, and ends at south pole. Travel at north pole and ends at south pole, and again from south to north inside it is. Like that, the field lines will be. Okay. So remember one thing, if you take a magnet, okay, outside the magnet, how the field will be? North pole to south pole. North pole to South pole. Look at here, where to where it will be? North pole to south pole, and here north pole to south pole. So if you take a bar magnet or any magnet, how the field lines will be? North pole to south pole will be outside. And what about inside? The magnetical field lines inside is that south to north. Okay, remember only one thing, north pole to south. Okay, outside, and inside south to north. North pole to south pole, outside. NSO. North pole to south pole, outside. South pole to north pole, inside. Okay, NSO is that outside. SNA is that SNE. SNE. South pole to north pole, inside. North pole to south pole, outside. Okay, NSO means National Science Organization. National Science Organization, and north pole to south pole, outside. SNE means NSO conducting by SNE. SNE means south pole to north pole, inside. Okay, look at here, magnetical field as quantity has both direction and as well as magnitude. Okay, magnetical field lines has both magnitude and as well as direction also. Okay, how you calculate a magnitude of the magnet? How can you calculate the magnitude of magnet? So magnitude of magnet is nothing but how the attraction force will be. How the attraction force will be. For suppose, let us take this is a magnet. I am placing a pen here. How the attraction will be? How the attraction will be? It is attracting very quickly. Then magnitude is maximum. Attracting slowly, the magnitude is minimum. Okay. So how can you calculate the magnitude of a magnet? How the attraction force will be? It is less or more. Okay, when the force will be maximum, when the force will be minimum, how can we calculate the force of magnet? Okay, it completely depends upon the field lines. Field lines. Okay, all the field lines are together. All the field lines are together means how the force will be? Is a maximum amount of force will be present. Okay, when the force will be maximum, if it is crowd, the force will be maximum. Okay, if it is not a crowded places or not a crowded magnetical lines, how it will be? A gap is there between one magnetic line to another magnetic line, it will be weak only na. In a family, if all are together means it's a very strong family, right? In a family, there is a gap between all, then it is a weak. If any person will come and defeat the family, right? So here also how it will be? The magnetic field lines has both magnitude and direction. Magnitude is there, that we know. It shows the north and south directions only. Right. So if I am taking a compass, what are the directions? So north and south directions only. It is having directional property, right? It is having directional property na? And it is having magnitude also. Both magnitude, direction is there. Next, the direction of the magnetical field taken to be which pole to which pole? North pole to south pole. Okay, north pole to south pole. North pole to south pole. The direction of the magnet will take it from north pole to south. Okay, next, and this north pole to south pole we taken as a convention of the magnetical field, because inside the magnetical field line we cannot show in a exactly, right. If I am taking iron filings around the bar magnet, how it arranges? From north pole to south pole it arranges. If I place compass also, how it will be? At end of north pole, the magnetical compass showing south. It means north, south. North to south it is coming, right? It's outside. So, for conventional purpose or easy purpose, okay, we are taking from north to south pole outside. Next, inside of the magnet, where to where it will be? South pole to north pole, as we discussed earlier. Okay, and forms closed curves. Remember the point. It forms that closed curves where if you take a bar magnet, north pole is here, south pole is here. North pole is here, south pole is here. Where it is started? NS4, remember, north to south outside. Who is conducting? SNE. SNE. So north pole to south pole. Direction outside. South to north inside. It forms a curved loop na. It forms a curved loop na. If the loops are number of loops are like this, okay, between one field line to another field line, the distance is very less, means the distance are less between the magnetical field lines, then strength will be maximum. How the strength will be? Strength is maximum. When strength is maximum, if it is a crowded field lines, if it is a crowded field lines, the strength is maximum. If it is not a crowded, the strength is minimum. Very simple. Okay, you all are together, no one will come to defeat you, right? If you are not together, definitely someone will come and defeat you. Okay, next, the degree of closeness of the field lines. How can you calculate the strength? The degree of closeness. How many close lines? Okay, how many close lines? See, if I am taking a bar magnet again, north pole to south pole, field lines will be like this. You see how the field lines will be very close. How the field lines will be very close. If it is very close, it attract easily because the strength depends upon degree of closeness. How it closes. Okay, how much closeness is there, that much attraction is there. Clear? Next, the field is stronger. The field is stronger. If it is a crowded, means the field is stronger. If it is not crowded, there is a gap, there is a distance between one field line to another field line, the field strength is that less. Okay, next, remember the point, no two field lines are attract each other or intersect each other. There is no two field lines. Okay, I'm taking one field line is here, another field line is here, coming, okay, and meeting at a point. If it is meet at this point, means the one ray is coming like this, right, and another ray is coming like this. So having two direction at this point, how it is possible? How it is possible? The magnet, how it shows, that always shows outside north to south, that we know, right? If these field lines intersect, means, okay, let us take a point P. Let us take a point P. From one line is coming like this, another line is coming like this. If these two are intersected at this point, how the directions will be? Two directions. At that particular point, two directions are there. Is it possible? Two directions in a magnetical field line. The magnetical field lines north to south is that is outside, inside south to north. From where it comes? The two directions when the two lines are intersect. It never intersect. Okay. So the compass needle would point towards two direction, which is not possible. There is a point of intersection of magnetical field lines. Okay, one line to another line cross each other, means at that particular point it has to show two directions. It is practically not possible. Okay, maybe in the examination if they ask you, means what is your answer? Anybody from comment section? Magnetical field lines are never intersect. We ask you reason also. Why it never intersect? If it intersect, it's showing two direction. Practically, it's not possible. So, the magnetical field lines are never intersect. If it is intersect, it has to show the two directions. Clear? Okay, this is simple. Next, your favorite time came. Why does a compass needle get deflected when brought to a near bar magnet. Okay, the very basic question, right? Very basic question. What they ask you? What they ask you? Why does a compass, what it is present in compass? Magnetic needle is present. Magnetic needle is present. Okay, magnetical needle is present. So this magnetic needle is deflected when near a bar magnet. Compass needle means what? Magnetical needle only. Compass needle means magnetic needle only. I am taking a bar magnet first of all as per the question. North pole is there, south pole is there. Where to where field lines will be? North pole to south pole. North pole to south pole. The field line is like this. North pole to south pole. North pole to south pole. The field line is like this only. Okay. North pole to south pole. This is the field lines, right? This is the field line. If compass is coming, so I am taking a compass here with a magnetic needle. Okay. I am taking a compass here with a magnetical needle. See which pole it is? North pole. Which pole it is? North pole. Which pole it is? South pole. North pole, south pole. It's coming towards north. What happened? What happened? North pole, north pole. North pole, north pole. South pole, south pole. Having same behavior na? How north pole is working? The another magnet north pole also the behavior is same, right? How south pole of the bar magnet is working? The another magnet south pole also same only. The behavioral is same. Then how it will be? How the force will be? Repel each other. Repel each other. I am taking opposite north south, south north. How the force will be this time? Attract each other. Attract each other. So whether it is repel or attract, whatever it may be, whether it is attract or whether it is repel, whatever it may be, the magnetic needle is responding or not? Yes, the compass needle is responding. Why compass needle is responding? Because it is also made up of a magnet only. Okay, so this compass needle, why it is responding? Because it is enter into the field of a bar magnet. Then the compass needle is made up of also magnet only. The compass needle is also made up of magnet only. That's why it's showing deflection. That's why it is showing deflections. Otherwise, there is no deflections at all. If I am taking a wood, for example, wood is entering in the magnetical field. It will respond? No. It never responds. Plastic is enter. It responds? No. So, which material responds that? Conducting material will respond because domains are present. Or magnetical materials are respond if it is entered in the magnet. Attraction or repulsion, these two will take place na. Which poles attract? Opposite poles are attract each other. Which poles repel? Like poles are repel each other. Okay. Next, define a magnetical field line. Define magnetical field line. Define magnetical field line. Simply, it is an imaginary. Simply, it is an imaginary line. At a particular point, it has both magnitude and direction. That's it. Very simple. Define magnetical field means how can we define it is that? Huh? How the magnetical lines produces? By the magnet only. Can we see that magnetical lines? Is it possible to see? No. It's an imaginary lines only. Na? When the iron fillings are around the bar magnet, then only it is possible to see. Right. Otherwise, if I am taking a simple bar magnet in my hand, around the magnet field is there. But can I see that? Is it possible to see? It's not possible. Okay. So, magnetical field lines are imaginary lines and it forms a closed loops. Okay. That's it. Remember that. Next. Very interesting topic. Magnetical field to current straight conducting wire. Okay, magnetical field produced by straight conducting wire. So let us take, this is a conducting wire, assume it. Okay, this is a conducting wire, and through the conducting wire current is passing. Through the conducting wire current is passing. If current is my thumb finger, okay, representing that current is representing with the thumb finger, and the curl fingers are, see, current is going upward direction, right? Current is going upward direction. So how can I represent, if electrical field is there, magnetical field is there, how can we represent the two fields at a time? Hmm? If I need to explain to others also, how can I explain the electrical field is this direction or magnetical field is this direction? Is it possible to explain? Is it possible? It's very difficult to remember, first of all, right? How the electrical field will be, how the magnetical field will be, which direction. It's very difficult. That's why we have to follow that right hand thumb rule. Okay, right hand thumb. So right hand only. This is my right hand and thumb rule. Okay, so this thumb is representing the direction of current. The thumb is representing the direction of current. And what about the curl fingers? See, okay, I'm twisting my hand. Okay, I'm moving like this. Thumb finger is always showing this direction, whether it is the curl fingers moving or not. What about the thumb finger? It always showing upward direction, right? So thumb is that upward direction, and the curl fingers are pointing like this. Okay, so how these two will be? What is the angle in between these two? What is the angle in between these two? 90 degrees. So electrical field and magnetical field are mutually perpendicular. Okay, electric field and magnetical field are, see, the current is this direction na? Current is this direction. Which one represented? Thumb represented. Which thumb? Right hand. That way, right hand thumb rule. Okay, that's why it is called as the right hand thumb rule. So the, see, wire downward direction. Thumb, current. And what about the curl fingers? Curl fingers. Curl fingers are represent magnetical field lines. Okay. See, if I am taking a one point here, okay, one point here, at this point current is there. From this point to, I draw one perpendicular line. I draw one perpendicular line. So how the magnetical field will be? Perpendicular to the circle, right? If I am taking a circle, if I draw any point on the circle, how it will be? Perpendicular na? How it will be perpendicular? So electrical field or current or magnetical field, both are perpendicular each other. If you want to define the direction of these two, which is electrical field and which is the magnetical field, see, the current direction is thumb. The current direction is thumb, and the curl fingers are the magnetical field. Current direction is thumb. Okay, for suppose if the current is going upward direction, which direction the current is there, thumb is that direction. If current is going this direction, thumb is this direction. If the current is going this direction, thumb is this direction. So which direction? Okay, remember, it is in a straight carrying conductor. It is in where? Straight carrying conductor only, because in a straight carrying conductor the current is straight. Okay, so in a straight carrying conductor, how the magnetical field, if current is represented by thumb, okay, magnetical field are represented like this. If it is going like this towards me, magnetical field is towards me. Okay, if it is going up, towards you. If it is going down, like this. So which rule we have to represent? Right hand thumb rule is the way to representing that whenever a current passing through a straight carrying conductor. Okay, or else you follow the screw rule. Or else you follow screw rule. Screw rule. See, if I am taking a screw like this, top of the part, if I am inserting the screw, which direction have to be turned? Okay, right side na A to B have to be turned, because fixing means it will be inside, na screw will be inside, right? Or else if I'm taking an anti-clockwise direction, it will be fit into the page. Anti-clockwise direction, screw will be outside now. So remember two, right hand thumb rule or screw rule, both are same only. Screw you taken means putting inside means that is the direction of the current, and magnetical field is like this. If screw is outside, how it will be? How it will be? Left side only, now have to turn screw. So left side turn and it's coming out. Okay. Next, see, when current passes through the straight wire, the magnetical field lines forms a concentric circles. How the concentric circles? When concentric circles you produce in magnetical field, when concentric circles you produce magnetical field, if current passing through a conductor, okay, a current passing through a straight conductor, it produces a concentric circles. How it will be? See, look at the diagram. Circles will produce. Okay, and we will follow right hand thumb rule. Right hand thumb rule. Okay, thumb point is that, thumb point representing current and curl finger represent the magnetical field lines. Remember, only thumb fingers, thumb current, magnetical field. Okay, next, strength of the magnetical field. Strength of the magnetical field. What it gives strength? How attraction will be? How repulsion will be? How attraction will be? How repulsion will be? It depends upon strength only, na. Strength is nothing but how it is attracting a magnetical material, how it is repelling a same, right? So strength is nothing but how it will be. So this attraction or repulsion depends on what? Attraction or repulsion depends upon the current in a conductor, and inversely proportional to the distance of the magnetical field lines. Okay, see, for example, I am taking a conductor here. Which direction current will be? Which direction current is? Upward direction. Current is upward direction. Now, how can we represent the magnetical field? Which rule we have to follow? Right hand thumb rule only, na? Thumb and magnetical field lines are like that only, right? See, for suppose if I am taking a current is 2 amperes, if I am taking a current is 2 amperes, I will get, for suppose I will get B is the magnetical field. If I am taking a current is 4 amperes of current, I will get same magnetical field or another magnetical field. First I am taking a 2 amperes of current. Second I am taking 4 ampere, double taken. See, if I am taking a 2 amperes of current, how the flow will be? And if I am taking 4 amperes of current, the flow is same or different? Flow changes, na? 4 amperes, magnitude of the current changes, right? So, if current changes, flow changes, right? If current is nothing but flow only, na? Flow changes. Okay, moving fast. How it is moving fast? The magnetical field also like that. Remember I should experiment. If movement of charged particle, if moving of electrons or moving of charged particles produces electrical field. If there is no movement, no magnetical field, right? So current is high, magnetical field also high. That's why magnetical field and current are proportional each other. Okay, current increases 2 ampere, okay, 2 amperes, 4 amperes, 6 amperes, 8 amperes. So current increases means flow also increases. If flow increases magnetical field increases. That's why magnetical field is directly proportional to the current. Magnetical field is directly proportional to the current. And coming to the second point, magnetical field is inversely proportional to the distance. Let us look at the diagram once. Let's look the diagram once. I am taking, this is the point, center point. Here to here I am taking R1. Here to here I am taking R2. Here to here I am taking R3. Here to here I am taking R4. Here to here I am taking R5. Okay. Here to here I am taking R6. So totally 6 radiuses are there. R1, R2, R3, R4, R5, R6. 6 concentric circles are there. Okay. So if I will place a one magnetical material, iron I kept at this point, and iron I kept it to R3. Okay. First I kept it R6, radius 6, and second time I kept it third circle. How the attraction force will be? Where the attraction force is maximum? At radius R6 or at radius R3? How the attraction force will be? How the attraction force at R3 and R6? Where the attraction force is maximum? Tell me. Anybody from comment section? Where the attraction force will be maximum? At R3 or R6? Tell me. Where attraction force is maximum? At a distance of R3 or at a distance of R6? Where it is? At R3, magnetical field is maximum than R6. Why the difference came at R3 and R6? Because R3 is less distance, then the magnet field is more. R6 is that more distance. That's why magnetical field is less. So B inversely proportional to the 1 by R. Okay na? So two factors. The magnetical field depends on the two factor. How the current will be in the circuit. If flow is maximum, magnetical field also maximum. Okay. If distance is less, magnetical field is more. Inversely. Understood now? Next. Mention the shape. Mention the shape of a magnetical field lines around a current carrying straight conductor. Anybody from comment section? Anybody from comment section? So as I told you, right? What is the question? Mention. What do you want to mention first of all? Shape of the magnetical field, right? Shape of the magnetical field. The magnetical field depends upon the flow of current, right? Flow of charge depends upon the flow of charge. Depends upon the flow of charge, right? Depends upon the flow of charge. Magnetical field lines. Just now we discussed na. Current increases, flow increases, magnetical field increases. So shape. So shape depends upon what? Shape depends upon what? Shape depends upon the conducting material. How the conducting material, whether it is straight or circular or triangular or any other shape. Okay. Next, which one they given? Straight conductor. So let us take a conductor is very straight. Let us take a conductor is very straight. Okay. So which direction? Tell me. Which direction? Can we take upward or downward? Your wish. Which direction we take? Anybody from comment section? Upward we take or downward we take? That is your wish. If you take upward or downward. For example, okay. So let us take upward. Okay. As per the comment, we will take upward only. So I am taking current is upward. Then what about a magnetical field? Which rule I have to follow? RHT, right hand thumb rule. Okay, magnetical current is upward. So current direction, finger, thumb finger, and curl fingers are this side now. Curl fingers are this side. So here it is entering point and here it is exit point. Okay, form a complete circle, right? Here it is entering. See, look at my hand. The curl fingers entering this side. Okay, and leaving out. So this is outward. This is inward. Okay. So mention the shape of the magnetical field. How the magnetical field forms a forms a forms a concentric circles now. That's it, simple. Forms a concentric circles only. Okay. Next, look at here. Magnetical field due to current carrying circular loop. Magnetical field due to current carrying circular loop. Look at the diagram. How the loop will be? Circular only, na? See, here it is entering. Here it is entering, and here it is that leaving a current. Just now we discussed about straight carrying conductor, how the magnetical field produces. If you take straight carrying conductor, how the magnetical field will be? Concentric circle, na? Just now only we discussed, right? And how the traveling of current here through a loop, right? So how the magnetical field will be? How the magnetical field will be? See, remember, current carrying conductor is straight. Okay, conductor, how it is? Straight. Straight. Okay, conductor is straight. And how the magnetical field? Perpendicular, right? So it means form a concentric circle. Okay, conductor is straight, forms a concentric circle. For example, this conductor turns into a circle. Conductor is straight, magnetical field is circle. If conductor is circle, magnetical field perpendicular, right? If I am taking a circle like this, if current is passing, see, current is passing, which one? Curl fingers are represented. Current is passing like this. Current is passing like this. And how the magnetical field will be? How the magnetical field? Perpendicular na. Perpendicular na. See, here it is entering current and here it is passing. Here it is passing. How that will be? Anti-clockwise direction, right? Anti-clockwise direction. How the field will? How the magnetical field will be? Perpendicular, right? How the field will be? Current is like this. Current. Curl fingers are current right now. And what about the thumb finger? Perpendicular, right? Curl fingers are current and thumb is the magnetical field. This time, when you take a loop, okay, conductor means like this. Conductor, field. Now, loop we are taken, right? Loop. So, loop. Through the loop, current is passing. Through the loop, current is passing. Which direction? Towards me. And magnetical field outside. Magnetical field outside. See, in each of every element in a circular loop, every element in a circular loop act as a straight conductor. So if you take straight conductor, how the field will be? Circles, right? If you take a straight conductor, how the field will be? Circle. Okay. See, every element is conductor only. Every element is conductor only, right? If I'm taking this small element, how it will be? Separately I'm taking like this straight conductor only na. If I'm taking this part, element means small part we take it. Element, straight conductor only na. So let us take this one, straight conductor only na. Direction changes, but if you combine all this, you will get a loop. So each and every part act like a conductor only, right? Straight carrying conductor. So straight carrying conductor, how the field lines will be? Circular loop. So see, every element is act like a straight carrying conductor only. See here you get curved lines, and when it is going up, what happen? See here, how it will be. Okay, lines will be changes now. Look at that. When it is comes to the middle, from the bottom, from the top, when it comes to the middle, look at that. Look at that. It's very straight. It's a very straight. So how this straight line will be? How this straight line will be passing through? If you take a circle like this, okay. If you take a circle like this, okay. If you take a circle like this, passing through right, okay, and it means it perpendicular na. It is perpendicular. Look at that north south. Look at the north south pole. It is perpendicular, right? If you take in a loop like this, how the field lines will be? Perpendicular na. See, field direction. I'm taking like this. Field direction, how it will be? Perpendicular. If circle is like this, field direction, north pole. Okay? Okay na? See here, when electric current passes through a circular loop, when electric current passes through a circular loop, it it creates a magnetical field that we know, right? Electricity passes, magnetical field produces. Electricity pass, magnetical field. No electricity, no magnetical field. Okay. Next, see, concentric circles. Okay, concentric circle. Every small section forms that circular loop only. Every small section is act as a straight carrying conductor only. Na? That means every conducting element produces a circular loop. Okay, and it forms a concentric circle. Whenever the circle is going up, at middle, it will be straight line only. From the bottom also, from the top also. Okay. Next, straight line at the center. How it will be? How it will be? Straight line. Straight line. It means completely perpendicular to a loop of the conductor. Okay, how it will be? Perpendicular. So that means electrical field and magnetical field both are always perpendicular. Okay, remember electrical field, magnetical field, both are perpendicular each other. If you take straight, perpendicular, circular loop, that is also perpendicular. Okay, center as straight lines, perpendicular direction. Look at this. Just now we discussed. Okay, this perpendicular to the plane of the coil. So through the coil, what it is going? Current. So coil, for the coil it is perpendicular, means for the direction of current also perpendicular. Na simple logic na bhaiya. To the coil it is perpendicular, means in coil what it is present? Current is present. To the current also it will be perpendicular. Na? Simple. So yeah, near the center of loop, the magnetical field is very nearly uniform. Okay, nearly uniform. See, from the bottom, how it will be? Like this now. Like this one. Whenever it is going, it forms a uniform lines. Where it will be uniform? Where it will be uniform? Remember, where it will be uniform? Where the magnetical field lines are uniform? At center. At center, the magnetical field lines are uniform. from bottom to top or top to middle, bottom to middle, top to middle, whatever it, okay, where the magnetical field lines are straight at center of the coil, okay. Next, magnetical field due to a current solenoid. Most of them are confusing about what is solenoid. Most of them don't know about a solenoid. What is solenoid first? Right? What is solenoid? Thinking in your mind. What is solenoid? What is solenoid? What is solenoid? Get any idea? Any idea? Solenoid means what? Any idea? Hmm? See, solenoid is nothing but just take a copper wire wounding like this. Okay, spring you know na. The spring made up of copper wire is solenoid. That's it. A spring made up of a copper wire. The number of wounds will be there, right? Number of wounds will be there na. That only solenoid. Or else just take a helical spring. That is solenoid. Okay. See, if you take a solenoid, magnetical field due to a current solenoid, magnetical field due to a current solenoid. See, here I am taking a wire wounding like this, okay, and in between the wire what they placed, soft iron they placed, what they placed, soft iron they placed, okay. Are you getting any doubt here? Are you getting any doubt? Huh? They taken a wire, around that inside the wire they keep a soft iron. Are you getting any doubt here? Anybody from comment section? Any doubt you're getting? No, sir. You also not getting any doubt? Why we taking soft iron here? Why you cannot take hard iron? Why soft? Because it is soft, na? That's why it respond. Huh? Yes. Soft iron means it will be easily magnetized. Soft iron means it is easily soft means easily we can handle, easily magnetized. Okay, that's why we take in soft iron. Okay, easily magnetized, easily demagnetized. If person is there, in the person's also, you know, behavior, right? Somebody is very simple and very easy to handle, and somebody are very tough, like you. Okay, so why we take in soft iron means it is easily magnetized and easily demagnetized also. That's why we take in soft iron. So what we will do here? We will magnetize that soft iron and it behave like a electromagnet. Okay, a magnet made with the help of electricity is called electromagnet. No need of specified definition. You know simple magnet na? I need a magnet, right? So if I would like to prepare a magnet means how can I prepare the magnet? I am taking a soft iron, bonding with a copper wire and given electricity. This soft iron is behave like a electromagnet because bonding with the copper wire na, through the copper wire electricity is passes. If electricity is passes means magnetical field produces na. Because of this magnetical field soft iron is magnetized. How it is magnetized? With the help of electricity. No electricity, no magnetism. So it is electrified, right? Right. So this is called as electromagnetism. Okay. Yeah. See here, the field lines of the magnetical field lines through around a current carrying solenoid. See how the field lines will be. How the field lines will be. From this one away, right? Away. And here it is entering. Have you seen the same diagram? Have you seen that same diagram anyway? Remember? Think of it. Just take 2 seconds. See, from this, here we take in a solenoid. Solenoid we connected to a battery. Okay. Solenoid we connected to the battery. Whenever we connect it to the battery, the current is passing like this. continuously through all the loops, and it releases a magnetical field lines. It forms a magnetical field lines, north pole and south pole. See, coming out, out. Here it is in, out, in. Where you see? From the comment section, got the answer. Bar magnet. Bar magnet only na, magnetical field lines outside. Which pole? North pole. Magnetical field lines inside. Which pole? South pole. Out, North pole. In, South pole. So it is behaving like a bar magnet. Bar magnet. Okay. It is behaving like a bar magnet. In a bar magnet, we keep soft iron. We keep soft iron. We keep soft iron. This soft iron is magnetized. Okay. For example, see, have you know about hypnotism? Hypnotism, you know, na? Look at my fingers only. Observe my fingers. I will hypnotize you. Right? So, is it possible to hypnotize all the people? Not an easy right. Who are having weak mindset? Who are having weak? Those people, it is very easy. Okay. A small mindset, that means it's very weak or depressed some people or a weak minded people. We can easily hypnotize, na? Right. Look at my hand, look at the direction, see. We can hypnotize, right? So here, if you need to hypnotize a person means everything and under control, right? So here also soft iron where we place it, under solenoid. Then soft iron also become a magnet now. Soft iron also become a magnet only. The process we call electromagnet. Okay. See here, how it is solenoid behave like that. Solenoid behave like that. Remember that. Solenoid. Solenoid behaves like a bar magnet. Look at the field inside. Look at the field inside. How the field is inside. How the fields are uniform field lines. How the field lines are uniform. Okay. See, if you understand bar magnet, you understand about solenoid also. Because solenoid is behaving like a bar magnet. Sometimes in classroom, there is no teacher. Some students will come and behave like a teacher, right? Hey, sit, stand, don't go there, don't shout. Okay, don't talk anything. Okay, they'll be explaining few topics on the board also. If the teacher is not present, some student with passion, they come and teach or they will control like a teacher. Right? So behavior is there. Now when the behavior came, if the teacher is present, they don't behave like that. So here also, when the behavior comes, when it is magnetized, when the electricity passes through the solenoid. So if the electricity passes through the solenoid, that particular solenoid is behave like a bar magnet. Okay, and how the field will be inside the bar magnet? It's a uniform magnetical field. Okay, see, field lines of the magnetical field through around current carrying solenoid. North pole outside, in south pole inside it is that uniform magnetical field lines like a bar magnet. If you take a bar magnet, north pole, south pole, how it will be? South to north, how it will be? Uniform, right? See, a current carrying solenoid coil used a magnetical steel rod inside an electromagnetic process. You can use steel, copper, okay, metals you can use. Mostly we can take soft iron because it's very soft. Okay, next, a coil many circular tons of insulated copper wire of a cylinder is called solenoid. Simply, solenoid is nothing but Solenoid is nothing but a copper wire with the shape of spring. A copper wire with a shape of, so many turns na. Many circular turns are there, right? Many circular turns are there. Copper wire, copper wire. That is acting like that, we call as that solenoid. Solenoid is nothing but a spring shaped copper wire is called, a spring shaped copper wire is called solenoid. Okay. So which material we take in here? Copper we take. Are you getting any doubt? Hmm? Are you getting any doubt? Sir, why we take in copper only? Why we cannot go for aluminum? Hmm? See, aluminum wires we will use in transmission of high transmission of lines from one place to huge distances. I will use aluminum wire. But copper wire, where we will use? In domestic purposes only we will use. Okay. Domestic purposes we will use copper wire, or going from one place to another place, transmitting lines, there we will use aluminum. Okay. Next, one end of the solenoid is behave as a north pole, other end is absolutely south pole, because there is no single pole exist. Two poles, one is north, one is south. Okay. Which is north, which is south, you may confuse. Which is acting as a north pole, which is acting as a south pole in a solenoid? Comment section give an answer also. Which is, how can you find out? Which is north, which is south? Field lines are out, north pole. Field lines are in, south pole. Okay. In means south pole. Out means north pole. Bar magnet only, behave like bar magnet means, bar magnet behavior how it will be? North pole outside, south pole inside. That's it. Okay. So, yeah. Then the magnetical field is same at all points. Where where the magnetical field lines are same? Where? At center. At center, how it will be? Parallel na? Parallel means what is the meaning of that? Parallel means what is the meaning of that? At every point is same only. Okay. Next, the field is uniform inside the solenoid. How the field will be? Uniform magnetical field. Where? Inside the solenoid. Outside is not uniform, because direction is changing, right? Okay. Direction is changing. How it will parallel? How it is uniform? Okay. Inside the solenoid it is uniform. Next, a strong magnetical field produces inside a solenoid. Which field is produces? Strong magnetical field. Which field is produces? Strong magnetical field is produces. You know why it produces strong magnetical field? When it is produces strong magnetical field, in previously we discussed, right? If current increases, magnetical field increases. That means when the magnetical field is much strong, when the magnetical field is much strong, huh? When it boosts, when it is having overlap, that time, huh? So a strong magnetical field produces. How it is possible to produce strong magnetical field? Because where it is produces in solenoid, solenoid is nothing but number of turns are there, na? If number of turns increases, magnetical field increases. Have a relation with the number of turns. Current increases, magnetical field increases. That we know. If you increase number of turns, magnetical fields also increases that many times, right? Okay. So that's why magnetical field is very strong, because it forms closed loops. How it will be inside solenoid, parallel, close to each other. Okay. Next. Which material we use? Which magnetical material we use? Soft iron. I already told. We already discussed why we use soft iron. Because it's very soft. It can easily respond easily. Response. If it is magnetized easily, demagnetized also easy. That's why we are using soft iron. If current is there, magnetized. Current not there, easily magnetized. Okay. If you on the fan, how it will be? After few seconds it off. If you off the fan, after few seconds only it off, right? Soft iron is not like that. If the electricity is on, magnetical field is on in a solenoid. Electricity is off, magnetical field is also stopped. Okay, that's why we're taking soft. We treat with only soft persons, right? Okay, so the process what we call an electromagnetic process. What is meant by electromagnet? A solenoid, okay, is electrified and it behave like a magnet. Electromagnet, electromagnet by the process of electricity, by electricity process, a material get magnetized. A material get magnetized. It's called electromagnetic. What we take in soft iron. Soft iron is behaving like a magnet. Soft iron is behaving like a magnet. Initially, it is a material. Soft iron is a material, right? So this material is behaving like a magnet. When the electricity is present, if there is no electricity, no magnetism. Then no electromagnet. Okay, electromagnet is nothing but a material. A magnetical material is behaving like a magnet when the electricity is present. It's called electromagnet. Here you may get one more doubt also. Sir, we have bar magnets now. Why we take electromagnets? Where we will use these electromagnets? Are you getting any type of doubts? Hmm? If you are using a bell, doorbell or bells, it works on the electromagnetic only, right? Whenever current is present, when the electricity is present, then only it works. Otherwise, if you on number of times also, no response, because electricity is not present, magnetism is not present. Okay, see, what is a solenoid? Simply tell me answer, anybody from comment section. What is solenoid? Today comment section is very fast. What is solenoid? Solenoid is nothing but what? A number of turns with a copper wire, like a spring. And this one we connected to the battery, okay, or cell. That's it. Solenoid done. Solenoid nothing but number of turns. Number of turns. Okay, a number of turns is called solenoid only. Draw the magnetical field lines. So magnetical field lines means, see, if you not remember the magnetical field lines, just remember this solenoid is behaving like a bar magnet now. The solenoid is behaving like a bar magnet only, right? How the field lines at north pole out, how the field lines at south pole in, okay, outside, inside. Then keep like this. That's it, enough. One end is acting like a north pole, another end is acting as south pole. In between that, field lines will be parallel, uniform. That's it. That's it. Okay. Yeah. Current carrying solenoid. Current there means then only electromagnet. Current not there. Okay, it just says solenoid. Next, force on a current carrying conductor in a magnetical field. It's a very interesting and confusing topic. Okay, very interesting. It just like understand only, but not understand after the class. Okay, so little bit focused, listen, especially this topic, because here if you take a conductor, through the conductor electricity is passes means electrical field is there, magnetical field is there, both are there. If this process under the magnetical field means again one more field is added, right? So here you may chances are to confuse. Okay, so don't worry, I will help you to solve that. See, where force on a current carrying conductor, where the conductor first of all in a magnetical field, where the conductor first of all in a magnetical field. See, I am taking a one conductor here. Okay, I am taking a one conductor here. If current is passing like this, upward direction, okay, current is passing like this in upward direction, and how the magnetical field be forms a circle, right? forms a circle na. Current passing forms a circle. Where these all the things in between, where these all the things takes place in between magnets. So I am taking north pole and south pole. Where to where field lines will be outside the magnet? North pole to south pole. North pole to south pole. North pole to south pole I am taken. Okay. In between magnets, what we place? Current carrying conductor we place. See, here you have to identify that which direction the force is acting. Whether the conducting material is experiencing a force or not, you have to see first of all. Okay. See how the conductor it is through the field perpendicularly is there. Okay. Conductor is like this. How the field perpendicularly. For example, conductor is like this perpendicularly. Colloidal na. Colloidal, right? So current direction is like this. Magnetical field direction is like this. So we arrange the conductor like this in a magnetical field. So magnetical field lines are passing like this. And conductor placed. Force acting na. Conductor passing like this, magnetical field is there. Force acting, right? So how the force will be? How the force will be? If force acting means how the motion will be. So these are the things. It's very complicated to find out without any rule, right? So that's why here we following the left hand. Which rule? Left hand rule. So in the left hand you just take three fingers: thumb finger, forefinger, middle finger. How these three will be? How these three will be means place the direction as per the diagram. Okay, thumb finger is upward and forefinger is like this. Okay, like this. See, like this. Thumb finger is upward, forefinger is like this, and middle finger is exactly perpendicular to the forefinger. See, thumb. Okay, let us take y-axis. On the y-axis, thumb. X-axis, y-x. Y-axis, thumb. X-axis, forefinger. Okay. Y-axis, thumb. X-axis, forefinger. And one more finger is there, right? Middle finger. Middle finger is towards you. Okay. Middle finger is towards you. Towards you. So, how it will be? Forefinger, thumb, forefinger and towards you. Towards you. All are perpendicular, right? Okay. So, forefinger. See in the diagram. What is this? North pole to south pole. On the x-axis. What is this? Field, right? So, field is forefinger. Field is forefinger. Okay. Field is forefinger. See. Field is forefinger. Field. Which finger I have to represent? Forefinger. Field. Current. 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 Middle finger. Right? See. If I am placing like this. Force. Field. Field. Current. Current like this na. Current is always representing like this, right? Field. Current is upward. Field. Current is upward direction. And the force will be RLC. Field. Current is see. See here. Field this side. Current is upward. And force will be how the force will be? Which finger represent force? Which finger? See. Field. Current this direction. Upward, right? And force will be perpendicular to both of them. Thumb. For example, this is the field. Okay. Forefinger is field. If direction of current is what? Direction of current. If direction of the current is downward, and how the force will be? How the force will be? This direction, right? Towards you, right? Field. Field. Direction of current downward. Conductor is downward. field is this direction. Okay, field is this direction. I am taking a direction of the current downward. So which finger? Middle finger, right? Current is that forefinger. Sorry, middle finger. Right. Current is the middle finger. Current is the middle finger. Field, current is side. Field is this side. Okay. Y, X. Field, current, and thumb will be. That means force is this side. Force is this side. Current, forefinger, field, and force will be current, field, 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 current, field, current, right? Force towards, towards. If it is changes, current direction changes means see, field is this side, current is this side, and force will be this side out towards you. And if direction of the current changes means force direction changes now. This time like this. Okay. Look at here. So when current carrying conductor is placed in a magnetical field, it experiences a mechanical force. It experiences a mechanical force. Which force it experiences? Mechanical force. That means it rotate. It rotate. Okay, because it is experiencing a force means it will be rotated, na? Or it will move, right? It has a motion, right? So how can we represent that? These all are Fleming left hand rule. In the Fleming left hand rule, which fingers we have to take? Thumb, forefinger, middle finger. Forefinger is that field, field. Thumb finger, direction of current. Thumb, force. Okay, forefinger right. Which finger it is that? Forefinger. Field direction. If field is upward, then we have to show like this. Next, current. Which finger? Middle finger. Four, current. Right? Four right. Four, current. And thumb is the force. Okay? Thumb is the force. Next, where we use this all? Electrical motor, electric generator, loudspeakers, microphones. Okay? Where we will use this? We will use generators, we will use electrical motors, we will use. Okay, how the electrical motor works? What is the principle of electrical motor? What is the principle of electrical motor? Electrical motor principle is that electrical energy convert into mechanical energy, na? Electrical energy converting into mechanical energy only, na? Fleming left hand rule is what? Fleming left hand rule is what? There is a electrical conductor where in magnetical field, electrical conductor in a magnetical field, because of this magnetical field, this electrical conductor experience a force. That force we call as that mechanical force. Right? How motor works? We giving electricity. Through the electricity, doing a mechanical work. Right? That only the principle of electrical motor. And generator is that right hand thumb rule. Okay, Fleming left hand rule we will use there. Yeah, right hand rule. Generator for generator, right hand rule. Okay, electrical motor, left hand rule. Left hand rule. We taken left hand rule only, na? Forefinger, right? Field. Thumb, force. Middle finger, current. Okay. Next, states Fleming left hand rule. Simple. Simple. How many fingers are there? Three fingers. What are they? Thumb, forefinger, okay, and middle finger. Thumb, forefinger, middle finger. Thumb, forefinger, middle finger. Thumb, force, a motion. 4, F, field. Middle finger, current. Okay, forefinger. like this. So field field okay, field is this direction. Thumb you take like this means thumb force or motion, and this is the current. Okay, field, motion, current. Okay, field this direction. See, field, thumb force, okay, current. Okay, current. Next, yeah, domestic electrical circuits. Okay, domestic electrical circuit. Already, we in the introduction part we will discuss it, right? So, if you are constructing an house or constructing any building, for that building, electricity is required, right? How can you connect it that electricity from where you will get? Hmm? So, this is a very important topic. Okay, you need to get easily marks the simple basics. Okay, see, if you observe the diagram very briefly, most of the electricity from where we'll get, from an electrical pole, right? From the poles only. From the pole we get directly. Huh? Where it will be? Through meter. See, which is this? Ammeter. Okay. From where you will get? Where you will get? Meter. Because if without a meter, how we know how much electricity is required for us? Right? So, look at the diagram. If you follow the diagram, it will be very easy. See, we take an electrical pole. From the electrical pole, where it is passes, how many lines are there? See, red, green, okay, this is black, center one is black, okay, three, or B, G, okay, or B, G, red color, black and green. So, three colors we will use, okay, even in your home also you may see these three colors only, mostly, right, red color, black, green, okay. See, from the ammeter where we taken? From the ammeter where we taken? See, one green wire, okay, one green wire. If you observe the green wire, what are you observing in green wire? Look at once. Look at once. If you take a green wire, okay, see, from the pole I am getting green wire, okay, from the pole. Through the meter, what it is coming? No green wire, okay. See, where it is connected, where it is connected to the main board only connected directly, okay, where it is connected, main board connected. From the main board, what we did? Earthing, earthing, earthing. So why we have to give earthing? Huh? Why we have to give earthing? Why? What is the use of earthing? Earthing is nothing but its protection. Earthing is nothing but protection. Sometimes you will get maximum amount of current, okay, sometimes short circuits, these all are there, right? So always for protection and all we give earthing. Even outside also sometimes there is digging a, beside the pole there is digging and connected to the wire, okay. So if any amount of electricity is there, wasted of electricity, that will be go down only, okay, because earth is having more capacity to take a huge amount of electricity also. We are not like that, right? Okay, and domestic purpose also, how much amount of electricity is required, that much only we will take now. If more come, what we will do? We cannot storage for tomorrow, right? Is it possible to storage in fridge? It's not possible. Okay, so earthing is the basic for protectional purpose. Next, remaining two wires, see, red wire and black. So, see, red wire. Red wire is what? Red wire is live wire. Live. Red wire is live. So, which is live in the wire? Electricity is present or not. Okay. Whenever you see an electrician, they will test the electricity is present or not in the switchboard. How they can test? By keeping finger. Huh? No. With the tester, they will keep right. So, if they keep tester, if there is an LED bulb, right? If LED bulb glows means it is a live wire. If it is not glow means it's not a live. Because if electricity is present, then only bulb glow, right? That's a basic na, right? When the electricity is present, the bulb glow. So if bulb glow means there is a live wire. Another one is what? Red wire is the live wire. And another one is what? Neutral. Another one is what? It's a neutral. Okay. And what about green? Earth wire. Red is live wire. Black is neutral. Green is that earth. Okay. Three wires. Red, blue, black, green. Okay. So red wire, live wire, black, neutral, green, earth. Green means earth. Okay. Yeah. Live wire, earth wire, neutral wire. Look at that. Live wire. What it is present? Red insulation wire is there. How can we? Red insulate. Why giving three colors means? If they not giving a colors, how can we identify which wire it is that? By the connecting or by touching, we cannot say, right? If you combine all these three, that's it, blast. Okay. If you want to celebrate Deepavali, eh, combining all the three wires, what will happen? It blast, right? We see that circuits, short circuits and all we will see, right? So how it will be happen? Combination of two wires, live wire and a neutral wire. Whenever it is connected, okay. So whenever it is connected, short circuit is present. Because of this reason only, if short circuit is produces means the entire thing will collapse now. Okay. So because of that, we giving earth wire. You see, sometimes we will use 3 pins. Why is that third pin is very big? Third pin enter means remaining 2 pins will be enter. Like if you see for a cooker, okay, and iron box or fridge, okay, which electronic devices are require more amount of electricity? For those only, because if it requires more amount of electricity, the problem with them only, more problem with them only, right? Right. With more problem, more electricity is there, more problem is there, because it get electrical shock with them only especially. Okay. So see, live wire, live wire, which is we taken red color. How much electricity, how much potential will be there? Remember, there is a chance to ask in examination, okay, MCQ, potential in domestic purpose is the 220 volts. Okay, this is also we are using for safety purpose only. Safety purpose we are using. Okay, neutral wire. What is the color? Black color. Okay, neutral wire. What is the color? Black color. And what is the potential it has? Zero potential. Neutral means nothing is present. It's a zero potential. Okay, earth wire. Earth wire. What is the color? Green color. Earth wire means with the help of metal plate deep in earth near the house. Okay, we are digging and connected to the metal plate under the earth. Okay, near the where we connected it, near the house we connected it, is that where we dig, where we require digging, and we will do that. Then after, a wire we connected with the help of metal plate, okay, on the surface. So through the metal wire The wastage of electricity, it passes through earth ring, right? Okay. Next, how much potential difference will be? How much potential difference? Potential difference between live wire, okay, live and neutral. How much potential is there? Live wire it is entering with 220 volts. Neutral wire is that 0 volt. Then the potential difference is that 220 volts. Potential difference means you know na, between any 2 points A and B. Here between live wire and neutral wire. Again Ln. Me only. Again between L and N. Okay. L is a live wire, N is a neutral wire. In between these two, how much potential is there? 220 volts. Live wire 220 volts entering neutral, exit. Okay. If electricity is enter means for exiting also we required one more wire, right? Huh? Where the electricity is passes closed loops only na. If it is a open loop, there is no electricity. Okay. For electricity purposes and all, we need only closed circuit. Current is entering with live wire. And how it go back? How it go back? With the help of neutral wire only. Okay. Neutral wire. And look at that frequency. Frequency. What is the frequency? 50 Hz. What is the frequency? 50 Hz. What is the frequency is that? 50 Hz. Why it is 50 Hz? Anybody from comment section? Why it is 50 Hz? What is mean by Hz? It's a unit of frequency. What is mean by frequency? The number of oscillations takes place. Number of oscillation takes place. If you take a photograph of the light, it will be oscillate. It will be oscillate. 50 Hz will takes. 50 oscillations will takes. If it is less than, our eye capture that oscillations and it will be effective for eye. So that's why the suitable frequency is that 50 Hz only. Okay. Next. Yeah. So this is the circuit diagram you need to follow in the examination time. Okay. You have to draw the circuit diagram for domestic purposes and all. From where you are getting here? See how many wires are there? Earth wire always green, live wire always red, neutral wire always black. The potential difference between live and neutral 220 volts. Why the purpose of air? Protection purposes and all. Okay. See from where? Electricity boards. Where we connected? Ammeter, because denoting the current and distributing the current. See how it will be parallel. If it is parallel means for each one potential is same only. For fan potential is same, for light potential is same. Okay. For other things also the potential is same. If the connections are parallel, the potential is same. Okay. You know that why potential parallel circuits advantages. If one is off, remaining all are work. Okay. With the same potential. Next, draw a schematic diagram of a common domestic electric circuit including a main fuse. Okay, very important question. Very important question for long answers. Okay, how many wires are there? Red, okay, green, black, green, red live wire, green neutral, green wire, earth, black neutral, live wire 220 volts, earth protection. Okay, neutral wire 0 voltage. That's it. Okay, diagram you have to draw it from where you are getting the 220 volts, from the pole to main board to ammeter, ammeter to main board. Okay, look at the diagram. Board, ammeter to distributing. Okay, so draw the diagram what we discussed now. The diagram you have to draw. Okay. Next, what is short circuit? What is short circuit? Okay, what is short circuit. When the short circuit will happen? Generally we know na, when two wires meet up, when two wires meet, takes a short circuit. Which are the two wires? Live wire and neutral wire. If you are enthusiasm to combine the live and neutral wire, you will get short circuit. Why? Why you will get short circuit? Why will get short circuit? Live wire, neutral wire combined means why it will takes place short circuit? Live wire potential how much? 220. Neutral wire potential 0. If you combine these two, okay, get short circuited. If the short circuited means I maximum amount of current passes. Maximum current amount of current is passes through the circuit. Okay. Maximum amount of current. So if maximum amount of current is passes means resistance is 0. Current is maximally passing, right? Because of this short circuit. Whenever two wires are meet up, short circuit only. Okay, when the short circuit is there, maximum amount of passes by the short circuit. Then blasters will be happen. Entire things will be collapsed because of this only. Okay. So live neutral, don't mix up. Don't mix live and neutral wire. If these two things are mixed means short circuit. Okay. Maximum amount of current is present. Next, overloading. Overloading. For example, I can able to manage 20 kg weight at a time. If I added one more 10 kgs or other 10 kgs, it's not possible to me, right? I will fall down. So here also overloading means I am connected to the fridge. Okay, I am connecting to the TV and I am connecting to the iron box or I am connecting to the other applications which are present. So at a time connected all. Then how it will be? How it will be? Load is increases now. Load increases now. That is called overload. Okay, in electricity also overloads are there. When the all the equipments are working at a set, then it will be overload. Okay. Yeah. Next, safety of fuse. What is the purpose of fuse? What is the purpose of fuse? Fuse purpose is what? Protecting purpose only. What is the purpose of the fuse? Protecting purpose. Okay. If electricity maximum amount of current passes means what? Entire thing will collapse now. That's why we will use force. That's why we will use fuse for protecting purpose. Nowadays we will use in place of fuse is that MCB. How fuse is connected? Fuse always connected in series only. Fuse always connected in series. In the electricity chapter we discussed about fuse and all. Okay. How the fuse is connected? Series. In place of fuse, now we are replacing with that MCB, miniature circuit breaker. Okay. Next. And we finally reached the end of this section. Once we recapitulate very quickly what we're going to discuss in today's session, right? So introduction of magnets, of electric, of current. Okay, relation between electricity and magnet. Electricity is there, obviously magnet is also there. Next, magnetical field lines. So magnetical field lines always forms a closed loops and never intersect. Never intersect. Okay. Next, magnetical field lines due to current carrying conductor. How the magnetical field lines? It forms a closed loops now. Concentric circles. Okay. In place of closed loop, write concentric circles. How it will be? Concentric circles. Next, magnetical field due to current through a straight conductor. Concentric circle only. Right hand thumb rule. Right hand thumb rule or screw rule. Thumb, current. Curl fingers, direction. Okay. Next, magnetical field with circular loop. Magnetical field with circular loop. How the magnetical field? How the magnetical field perpendicular to loop? How the magnetical field perpendicular to the loop. Next, Magnetical field due to current carrying solenoid. Solenoid means how it behave like when the current is present. It behave like a bar magnet. Next, force on a current carrying conductor. Which law we will use? Left hand rule. Left hand rule. Which fingers we take? Thumb, forefinger, middle finger. Okay. Thumb, force, forefinger, field, force or motion, forefinger, field, middle finger, current. That's it. Okay. Domestic electrical circuit. In domestic electrical circuit, which are present? We have three wires: red, green, and black. Red, live wire; green, earth wire; black, neutral wire. Okay, neutral wire. Earth for protection, black wire is for neutral. Send back to the pole again. Okay, or any other. Electricity is coming through red wire and it go back to the neutral wire. Okay, two wires are coming one wire, going one wire. In between these two, earth wire is there. Okay, for protection under. Yeah. Thank you. Today is the end of the section. I hope you all enjoy the section. I also enjoy with you. Okay. The rest of the things we will discuss in the next class.